Greetings everyone. I'm Abhijit Paul. I'm from University of Dhaka, Bangladesh, French graduate, and my work is a type-driven programming from task interfaces to the calculus of constraints. I'll begin the discussing what is prompt. Now, we all have used prompt. Literature has divided prompt into two parts, system prompt and user prompt. I'll focus on system prompt example here. The instruction is you're given two items, a sentence and a word contained in that sentence. Return the first of the speech tag for the given word in the sentence. The input is the cat at the hat and the category has the output is noun. So this is a structured system prompt. And for user prompt, it is our general question to the LLM. For example, what is dependent text system? Now, this distinction is necessary because system prompts are being widely used across commercial and research applications. For example, Duolingo, Apple Intelligence have services such as notification prioritization, agentic usage of mobile applications that likely uses it. So more concretely, we have numerous HCR and analytic literature and user structure. For example, from topic modeling, use articles. They essentially instruct the LLM to extract for a large data set and retrieve a structured output. So this is a canonical example of system prompt. And this description of system prompt is necessary. Uh, However, most of the prompt programming literature does not mention this distinction in their research. And the reason is the difference is often blurry. We can look at code generation. For code generation, if we ask LLM to generate some code, these can be considered user prompt. However, if we have a system prompt explaining our requirement programming language that is always fixed, in that case, it can be considered a system prompt. So the distinction is somewhat blurry. And most important characteristic of system prompt is that it is fixed. Like software, it occasionally it remains fixed for a period of time. And that is the reason why we think prior literature should mention system prompt because they intuitively uses system prompt, not user prompt. Because when you are compiling a program that is prompt, or when you are optimizing a prompt, when you are constraining a prompt using type system, you need a fixed prompt. If the prompt changes frequently, and those approaches become useful. So literature innately and inherently uses the system prompt. That's not explicitly mentioned. This is a caveat I just wanted to mention before going ahead. Now I'll look at the example of prompt programming. So we can have an example app called Duolingo, which is similar to Duolingo. Now in Duolingo, users can write a sentence. Duolingo will use LLM to get the further distance of the word that the user needs to. And then it will generate more examples for that parts of it. In this case, now, and show it to the user. As you can see, LLM is acting as a software component here. Given an input, it generates some output. Now, this is a very credible use of prompts inside a program, the software component. And these images are taken from Duolingo. And the final example is text to SQL. These essentially motivated this. When I was working on text to SQL, I had instruction like that, and then I would give a schema of the database, and it can come from a retrieval system such as RAG or role-based system. And then we have the natural language question and the SQL output. The important thing is the SQL output must follow SQL syntax. So this is a syntactic constant. And I was looking for a solution to enforce this syntactic constant for essentially output validation. And there are many open source tools. Proof tools use a simple type interface. For example, here the type of name is a string, hobbies is a string, very basic type interface. And there is VIML that essentially structures the entire prompt. So instead of plain string, you have structured kind of string. And then you have again simple type interfaces that determines what goes. And most importantly, if a polymer system or other type system natively available, you can compose really complex type systems in VML. And then I look what motivated the developers to use these type interfaces for prompts. And they saw this example. Traditionally, we would use to return HTML as a string, but now we use something more structured. And this is because, and I quote, the idea of maintaining hundreds of SS strings for prompts kind of systems. So maintainability is a concern that motivates structured prompts. And then we found more libraries. For example, lambda.txt uses a structured prompt much like a program. And instructor also uses a structured prompt. And tech giants such as Microsoft have also started projects on it. For example, TypeChat constructs prompts using type. And it also validates the response using schema or type system. And if the output does not conform to the type system, it prepares by prompting the LLM again with the error from type change. This is the example taken from the documentation. So as you can see, the output is well typed. Each of the values has type annotation associated with it, and they conform to this type structure. And recently, Stanford Energy has also entered this space with their big project TyDe'25. As you can see, they can compile prompts. So what does it mean to compile a prompt? You compile programs to be faster, to be more performant. Same goes for LLM. To compile LLM so that it gives the best result efficiently most of the time via searching. So this cp.compile function can compile prompt, much like a program. And they also use some structure here. So they don't use type system because NLP focuses on the analytical mode. So we have this three emerging philosophy. Maintaining hundreds of asset strings is annoying. So developers build libraries with structured prompts. Output required as a software component. So developers build type validation. And we need to compile the prompts to optimize the prompt. So developers build heuristics to optimize prompts. And we can map this literature into a traditional layered structure of the prompt program. So we have the input layer, the business logic layer, the output layer, and a program naturally interacts with many other components layered here as well. And we then map existing literature in each of the cells. And very surprising also, all of the boxes have priorities on it. So independently, developers are successful exploring many things, but they are conforming to a structure of the prompt program. And this finding started our research. And another recurrent pattern is the use of tag systems. As we saw in the previous example, almost all of the users provide they use tag systems for LLM output validation, constraints. So this is also an observation that our business hasn't pointed out. Now, the notion of prompt program not coined by us, it is already laid out there. Speech plan first mentioned this idea, however, mentioned it abstractly, and in this extended aspect, we solidified this understanding from the history. And most importantly, we show the use of tag system as a different pattern that hasn't been studied before. And to find more support as tag system is a recurring pattern, we identified 13 constants for prompt. And notice that 9 of them, 9 of the constants have been added, often in the form of tag system. And there are 4 constants that haven't been covered, domain constraints, tone constraints, etc. And we notice that there's semantic method. So literature has covered syntactic constraints, not semantic constraints. Now, this is a very terrible research direction. How we can incorporate semantic constraints, perhaps by a probabilistic study. As finding, we have prompt program that often uses tag, and we have prompt constraints often in the form of tag. So take tag-driven prompt programming. So it was all laid out here. So we formally define type-driven prompt program as a dependently tagged code calculus with probabilistic refinements that treats prompts as type programs and constraints and type refinements. We want to emphasize probabilistic refinements because to handle the stochastic nature of LLM, and most importantly, the semantic constraints we mentioned earlier, we need probabilistic refinements. And essentially, prompt program is a code tuple. We have the input output, and the prompt is essentially the LLM instruction, and the epsilon here means the parameters of LLM. For example, 10 parameters. And here's the constraint, type of constraint we can have. The 13 constraints can be here. And here's the example of how we can explain real world examples using this definition. So this is the text-based filter. We have the input with the constant is natural language, output with the constant valid solution and no verbal information. and LLM finally constant. So constant line here is a domain constant, which is a semantic constant that the output should only be our this domain, which essentially is a guardian rather than. And we also identify some focus on the research. So there have been six interfaces as we have found, so, and there are also parallels on decoding, which we'll discuss later on. And there have been also research in constraints along with the type interfaces. However, there have been few research on program optimization or program compilation, or reusing the whole program as a type system for end-to-end optimization. That hasn't been done yet. This is a credible research direction that this experiment has suggested. And then we have the input and output type. We'll discuss each of the layers now. So we have input and output type. So this is the input type definition, and here is a more type example. For example, coffee option quality can be light, regular, or an integer. So a simple type interface. Similarly, we have optimization of prompt. So prompt is optimized via summary, meditation, finding future examples that are most suitable, because LLM is stochastic. Just changing a word can impact the performance. So summarization, finding better examples, reordering, restructuring, this mutation helps improving, optimizing the prompt. So probabilistic, there is a lot of mutation, featured example picking, and text which mutation the best result, and they combine it to form the muted prompt. Now, this surface space is very large here. So what we propose is that this is just to show how much research potential type-driven form programming holds. So we show an example that probabilistic in the domain is large. We can add our domain-specific constraint to limit the search distance in very significant way. So we take some X from a distribution, we apply it to generate mutated program E prime, and then we check that we ensure that the mutated program conforms to our constraints. And we can also clone constant data. For example, if our constant need is enough, we only take the mutation that satisfies the constraints. So this is us applying the mutation that satisfies the constraint. And we can formulate it using a simple theorem that if our modified program comes from a mutation set that is valid, then it will satisfy context we have. And it has been rigorously studied. So for post-hoc constraints, it is done by validating the JSON schema against the type system. And if it is not validated, then we send it for it again. And we also guarantee that if our output is Y, the Y must be from the semantic constraint. And most importantly, there is constraint decoding. So constraint decoding is interesting, that we'll discuss now. So how LLMs generate output text by text, token by token. So what constraint decoding does is it masks the tokens that we don't need now, and then do it by offering type reachability. So it is used in programming language. So given the current code that has been generated so far, incomplete code, we generated incomplete graph of the program. And then we generate the number of reachable paths using that system. And we pick the ones that are most credible and mark everything in the output there. So this is an example of constraint decoding. And these approaches are what we use. But it also suffers from the constraint in the other layers. and also runtime monitoring. So in conclusion, we provided synthesis of this emerging idea from programming origin, right? But this notion of type system across literature. Currently, only fourth generation class uses explicitly type system or mentions it. However, we showed that open generic type system or prompt program. So there is this emerging trend between academia and open source industry using type system in prompt program. This is a core focus that the focus of LLM research has a tangential shift towards type system. And they found 13 constraints of the diversity of the prompt, and we identified 4 prompts that hasn't been studied before, a more semantic concept. And we also showed 3 examples how type systems can improve prompt programming using a constraint-preserving optimization. And we think it is a very interesting research direction, this extended abstract proposal, because LLM are using, and I'll end my discussion with a recent case. So GPT-OSS was released as open source software, and GPT spent millions and billions to ensure it is safe. However, developers broke it using simple perturbing. So we can't ensure enforcement of constraint via training. We need something like tax system to come to the rescue. For LLM from safety, from structure, from semantic, from syntax, tax system has come to the rescue. Are you good? Thank you. Do you have any questions? Just a quick one.
We also present our table up here. Before that, Abhijit, so could you turn on your mic so that you can answer question?
Yes, I'm available in my.
Have you tested your LM generated code against have any like test cases that demonstrates how often work? You hear me?
Oh, okay. No mic. Oh, little bit hard to hear the room mic.
Maybe I'll just ask them.
So maybe you can come here. And that's what President voice should be.
Can you hear me now?
Yes, I can hear you.
Okay, yeah, good. So have you tested your approach on like realistic scenarios? For example, do you have a set of test cases that shows how often could your synthesize the program, generate the type corrected programs?
We have experimented on the test we are doing, and we plan to submit our results soon. But it is not included in the presentation currently.
So is there
So for the text-based queries, we use the type system to repair the generated syntactic constraint, but it takes a lot of retries to get the correct syntax most of the time. So currently we are trying to improve it. How can we get the correct repairs at the minimum number of retries?
okay. Yeah, thank you.
Thank
Really quick. Afternoon. So
Hello, Abhijit. Can you hear me?
Yes, I can hear you.
So my experience with LLM is probably much less than yours. When I haven't actually asked the LLM to produce any code, but just like following up on the question that was just asked, if the code does not type check, and with my understanding that LLM, there's a kind of stochastic nature to it in the sense that when you ask the same question twice, you probably won't get the same answer, right? So in your experience, when you get something that does not type check or the code is obviously incorrect, is it worth it to ask it to try again?
Yeah, so if we give the error trace, most of the time it can generate a better result. So providing more context based on the error that we encountered typically improves result. It depends on how much context you can provide to the LLM. That really controls the output. So in practice, we saw that if we give more error trace, the output seems to be converge faster. So this
So the point is to give it more information, like the output of the error, the output of the compiler, like where the error is, and then it will iterate and maybe give you a more correct answer. Okay, thank you.